So he's going to talk about basically that it's really bad to plug USB things on your laptop. Good luck.
Thank you, Matt. So, like you said, I'm Jon Larimer. I'm a researcher on the IBM Exploitation. I'm a researcher on the IBM Exploitation Advanced Research and Development team. My primary focus is malware research. I also do some vulnerability research. I really like reverse engineering, so that's what I spend most of my time doing, reading a lot of assembly code and occasional source code. So my talk today is about USB auto-run attacks against Linux. And by auto-run attacks, I mean ways that you could cause code to run by inserting a USB device into your PC. And I gave a talk at Black Hat in Washington, D.C. about kind of generic USB-based attacks against Windows and Linux. And this talk is more focused on just specifically Linux. So I'll be talking about attacking the device drivers, file system drivers, down to the user mode level. So first I'll talk about auto-run malware. And the name comes from the fact that on Windows, you could have an auto-run.init file on the CD-ROM, and if you insert it into your PC, it would run whatever software was configured to run by that file. And this was made just to make computers easier for people to use, so you didn't have to click any buttons when you insert a CD into a PC. Eventually, it started working on USB also. They had the feature to enable application on USB. But it's, most people disable that now, and Windows 7 actually changed the way that the auto-run.init file works, and it won't run from USB drives anymore. But what we've seen is that malware and hackers can still take advantage of vulnerabilities. And one big example is the LNK vulnerability that Stuxnet used. And that was a problem where when Windows was trying to render the icon for an LNK file, it was able to load an arbitrary DLL and start executing code. Something else that we've seen is PDF previews, where if you've ever done any analysis of malicious PDF documents in Windows XP, sometimes you'll notice that if you click on a file, Windows will generate a small thumbnail, and sometimes that'll actually trigger the vulnerability in the malicious document, however you even try to open it. And another example is there was an embedded BMP thumbnail vulnerability that was made public at a conference in Korea in December of last year. So what about auto-run malware on Linux? So there are some desktop environments that support auto-run scripts on external media, and GNOME and KDE both support the freedesktop.org specifications. And those specifications allow you to put a file named .autorun, autorun, or autorun.sh in the root directory of a USB stick or any other file system. And whenever you insert that, the Windows system will ask you if you want to execute the script. Luckily, the specifications forbid running these scripts automatically, so there's no way to configure your Linux desktop to automatically run these scripts whenever it responds. It's always going to ask you, so that's something that they did a little bit better than the way the Windows handles it. So my focus was on taking advantage of security vulnerabilities. So the auto-run scripts are not really that important. So there, it turns out that there's a lot of code that executes whenever a new mass storage device is connected. And I was focusing on USB, but there's also secure digital SD cards, SATA, FireWire, PCMCIA. There's a lot of different there's a lot of different ways to mount physical storage on modern machines. So those subsystems all have device drivers. Those device drivers could have poorly written code. You never know. So if you can create a malicious device, you can take advantage of a vulnerability in a subsystem driver. It's pretty hard to pull that off. There's also file system drivers. For example, the kernel level drivers for the ext3 and ext4 file systems. And then there are the user mode drivers. For example, the NTFS 3G driver that Ubuntu uses. And another place to look for vulnerabilities is in desktop applications, such as in the file browsers and thumbnailer applications. And that's where the LNK vulnerability in Stuxnet was. It was an icon handler in the Windows shell. So a vulnerability could exist at any of these layers. So it's kind of important that these pieces of code get audited. It's not normally code that's audited for security vulnerabilities. So I can talk about attacks on physical systems, and it's usually considered, if you have physical access, game over. So a lot of people aren't really that concerned about vulnerabilities that require physical access, but there are a lot of mitigations. For example, full disk encryption. If someone steals your laptop or steals your hard drive, say if you have the disk encrypted, then it's pointless. So in that case, the only way to attack a machine with full disk encryption physically is by when the machine is already when the machine is already running and the user is logged on and the disk encryption is run, or the decryption routines are running. So a couple interesting vulnerabilities are for the IEEE 1395 or 1394, the FireWire physical memory access. If you have a FireWire port and FireWire drivers on your laptop, you can connect a device. The attacks that I've seen use the Linux PC, so you can actually read and write the physical memory from the IEEE FireWire port. And then there was also the cold boot attack, which was a couple years ago. So, but that requires being able to boot from external media or stealing the RAM or swapping out an internal drive. That was actually kind of interesting that one of the graphs in that paper was on stealing the memory. They would use Freon to freeze the memory to lower the temperature, because as the temperature warms up, it loses the data. So you can freeze the memory, pull the memory out of the PC, stick it in another PC, and then read the contents of the memory. So that's just another example of an attack on a physical system. That one's a little bit harder to pull off than. It's a little bit harder to do than the stuff that I'm going to talk about today. And then we have removable storage attacks. Most desktop operating systems will automatically mount file systems on USB. And if you're using USB, then physical access isn't even really that necessary. You can just find someone to plug a device into their PC. You can send them a USB key in the mail or leave one laying around and hope someone picks it up. So you don't really need physical access if you have a target. So, like I already said, if an exploit runs while the PC is already logged on, it's already booted, and the user is logged on, then you can use that to defeat full disk encryption. So I'll show an example of that. So some of the code that I spent some time looking at were the USB drivers on Linux. I think these have probably been audited more than some of the other code that I've looked at. They're a good target for fuzzing attacks if you have a way to fuzz them. I don't really have much to say about this slide because it's all talking about source code files. If you would like to spend some time analyzing how USB works on Linux, then this information can help. So there have been vulnerabilities in USB drivers in Linux before. There was a company called MWR Windows Security that found a USB driver bug in 2009, and it was a problem handling USB string descriptors. It was just a straight Stack Overflow. They also found another bug in another driver in March of this year, March 2011, in a different driver. So the same company with a different driver. They haven't actually written a real exploit for it. It was just a denial of service attack because I don't think they could figure it out. You can also fuzz USB drivers, and some other people have done work on that. Ortiz Jodier used a hardware and software solution using a custom programmable USB development board. Tobias Mueller used QEMU-based fuzzer, and that was in 2010. And it's pretty easy to, if you can actually write an exploit against a USB driver, it's pretty easy to exploit that with a cheap USB development board. There's a thing called the TZ-USB. It's a little device about this big. You can program it to act like any USB device you want. It's a programmable firmware. You can really do anything with it. So that's one way to get your exploit payload to your target. So I also looked at the USB mass storage class drivers. And these are the drivers that handle dealing specifically with mass storage devices. So the other USB drivers that I mentioned were the generic, they handle all USB devices. There's also a set of drivers that handle mass storage specifically. And those are, the way it works is by actually communicating with the SCSI subsystem. So there's not really much there. At the lower levels, the USB mass storage protocol uses the same commands as the SCSI, protocol. So it was pretty easy to write drivers for USB mass storage because most of the code's already there. So there's also some subsystems kind of in both user mode and kernel mode called UDEV, which is the device manager for Linux, which adds and removes entries in the UDEV directory. These can trigger events based on rules, or you can do use an IPC mechanism using a network socket. And there is dbus, which is another IPC mechanism. It allows applications to register for device events. So if you have an application that you want to know when someone inserts a USB drive, you can register for a dbus event, and any application at all can register for these. And that's what Nautilus uses, the known file system router. That's what it uses to get notified of new file systems that are mounted. And UDIS is just another layer. It provides a dbus interface for dealing with disk devices, and that uses another library. So it turns out there's a lot of code that's running it's all tied together here. So there's a lot of room for vulnerabilities to be hidden. Another layer that we can look at is file systems in Linux. And traditionally those were in the FS branch of the kernel source tree. So if you're looking for the source code for a file system driver, that's where you look. And file systems work between the low-level disk bus drivers, like the USB driver or the IDE driver, and something called the virtual file system, or VFS. And there is also Fuse, which is file system in user space, and GVFS, which is the known virtual file system, which is kind of interesting. It's pretty new. It's not really a traditional file system. It's used to provide support for accessing files over SMB or FTP or even HTTP through the regular user interface. So that's another thing that was added to make your computer easier to use, which has the potential for abuse. So there have been vulnerabilities in file system drivers before. There's a couple ways that they could be exploited. You could create a malformed file system image on a USB drive. And depending on which driver you're looking at, if you can successfully exploit one of these, you get root access. You have kernel mode access, which gives you a full run of the entire machine. If you're attacking a user mode file system driver, that usually runs in the context of whatever user mounted the volume. And so, for example, if you plug a NTFS formatted USB stick into an Ubuntu machine, it's going to be mounted as whatever user that you're logged in as. So you can't use the an NTFS driver vulnerability to get root access in the latest versions of Ubuntu. And these kind of bugs are actually pretty hard to exploit because if you don't already have local access to the machine, you could actually consider it a remote attack because you don't already know everything about the system. You might not even know which version of the kernel it is. So if you're relying on a kernel structure being at a certain address in memory, you don't really know if it's going to be there because you don't know what version the kernel is, or you might not even know which version of Linux is running. So it's pretty hard to pull something off like any sort of driver-based attack remotely. So if you're interested in looking for file system driver vulnerabilities, there's a couple different ways you could do that. One is just by manually auditing the code. You can read the source code and take a look at how the structures on disk are parsed, the low-level file system structure, and look for mistakes in the programming. There are a lot of static analysis tools out there, like Linux or CLang. It's pretty easy to get fuzzing working on the fuzzing file system drivers because any block device, even just a file, can be mounted as a file system. So you can just create a file system image, randomly modify bytes in that file system image, keep trying to mount it and unmount it, and wait for the kernel to crash. And there was actually a paper written in 2006 called Automatically Generating Malicious Disks Using Symbolic Execution. That was from Stanford. And it's kind of like fuzzing, but they used a lot of crazy academic intellectual techniques like directed graphs and symbolic execution. And it was actually pretty interesting because they were able to generate malicious disks. They weren't really that malicious because they didn't execute any code, they just crashed the system. But they were pretty successful in doing that. So now working our way up to more into the user land, user space. So known Nautilus is the file browser which is used by Ubuntu Desktop Linux and any other Linux operating system that uses GNOME. And it supports most of the free desktop.org specifications, which includes the Autorun scripts, but we don't really care about those. So the interesting thing is that by default, it'll automatically mount known file systems on USB drives. And whenever you insert a USB drive, it'll mount it in the media directory with a name that comes from the volume. So whatever name